Hi all, welcome. Thanks very much, Lewis. It's really fun letting me letting me do this with you. If this is something that you guys like, then just let us know because we'll do similar things before the next two exams as well. Okay, I think it's a really good way to kind of share this out. So Lewis is going to have a little bit of time to think about some of those questions, go back through your live feed, and I'll be doing the same. So I'm going to do half an hour with you now, and then I'm going to come back half an hour after the after Lewis's next feed, which is like I'm like the support act, okay? I'm like the kind of the Thrones extra or something after the Game of Thrones show. So I really listened to some of the things Lewis has been saying. It's great advice. It's a big message really about not panicking because the paper being as hard as it's going to be is going to be as hard for everyone else. You guys are ready, and I've been doing quite a bit of live streaming just recently this half term, and you guys it's been a pleasure to hang out with you because you're so well prepared and you're asking such good questions, and these are the questions that are coming up today. I'm going to go through systematic and random errors, which people have asked me for, potential dividers and circuit problems, thermal physics and the gas laws, homogeneity of units, okay, and sig figs and accuracy and Fleming's left hand and right hand rule. In some specs right hand rule comes up, Archimedes principle, and just basically some other exam tips. Okay, so I really hope that's really useful to us. Let us know if it is or isn't during the live feed, during going through these bits. I'll stop for chat every now and then, but let me know what you want me to go through in the next half an hour after Lewis's next feed, and I'll think about that while Lewis is chatting to you. Okay, so without further ado, let's jump into the visualizer and let's go through some of these things that I've got. Okay, so the first one was about systematic versus random errors. Okay, so there's only really these two types of errors in physics. So if one of your exams is coming up and you've got errors and things on that paper, then think about them as being these two kind of groups. These are some examples, right? Okay, so a systematic error could be a zero error, it could be heat loss, so not being particularly insulated, it could be friction, haven't compensated for friction, that type of thing. Whereas a random error is maybe a timing error. Normally human errors are random errors, digital meters fluctuating, or maybe like the random nature of nuclear decay. So think about them differently because you deal with them very differently. Now it tends to be the solution for these errors tend to be, for the systematic error, you've got to change your method somewhere, and it might be that you actually you put a variable that's changing somewhere as an intercept or as a gradient or something like that, so we can actually change the way in which we're processing the data sometimes, maybe to allow the gradient, the graph just to be shifted up rather than changing the gradient, for example. Okay, so there are ways that we can account for systematic error. It might just be as simple as you need to zero the meter, you need to deduct a certain value from whatever your measurements are each time if you realise it's a zero error. It might be about heat loss and actually insulating it. It might be about compensating for friction by sloping your ramp up. It might be about an air track or something like that. But random error, okay, timing error, normally the way to deal with these and repeats, anomalies and means can only deal with random errors. So if you identify, oh, that's an example of a random error, right? Well, state that you're going to repeat the measurement many times in different places maybe, and you're going to get rid of any anomalies and you're going to calculate a mean average, right? So other things with time error can improve the precision and accuracy of the actual things, but the main thing that gets rid of random errors is repeats, anomalies and means. Alright, I hope that was helpful. Next one is potential dividers and kind of circuit problems, because you know what, potential dividers are really examples of circuit problems. And potential dividers are really straightforward, but the thing about them is they come up within larger questions, and it kind of catches people out. And we're finding a lot in as examiners that people aren't recognizing the potential divider question. So I like to play spot the something question, right? So be on the lookout for potential divider questions. Another one that people don't tend to spot is the Newton's laws questions. Okay, spot the Newton's laws question in that exam. Think to yourself, okay, what is the content I've got to apply to these contexts? And that's something that Lewis talked about in today's live stream as well. Okay, well, potential dividers are really straightforward, really. This is the kind of simple setup, although it might not always look like that, because if you saw that, you'd probably recognize potential divider, but it might be just a normal circuit diagram, and you recognize as a pair of resistors in series. Maybe one is a fixed and one is an LDR or a thermistor, right? And all we have to do is make one ratio equal another. The ratio of the resistances is equal to the ratio of the voltages, and you can all do that. I'm absolutely certain of that. Okay, so just think about sharing this voltage, this potential difference out in the ratio of the resistances. Okay, it is that straightforward. And what do I mean by that? Well, okay, they are the same thing as circuit problems, but basically circuit problems have solutions based on two laws, or three laws, because there's Kirchhoff 1 and 2, Kirchhoff's current law and Kirchhoff's voltage law. But really bear these in mind whenever you get given a circuit. The problem is they may be giving you some of the details that you need, but not all of the details that you need. So you need to think to yourself, well, how can I figure out the detail that I know that I need to work this answer out, but that they haven't given me? And it's going to be by one of these two sets of laws, right? So in series, basically all the currents are the same. In parallel, the current through the power supply is equal to the sum of the currents in the branches. Okay, remember that's Kirchhoff's first law. Second one is that the voltage in a series circuit sums. Okay, so the voltage supplied to the circuit is equal to the voltages across all of the individual components. But in a parallel circuit, well, they've all got a direct connection back to the cell or the power supply, so the voltages are all equal in every single branch. So be thinking of this as your toolbox to solving circuit laws problems. The other tool in your toolbox is Ohm's law. So if you know the resistance of a component, you know the voltage across it, you can always work out the current through it. For example, they might tell you the voltage and the resistance, but you know you need a current. So how do you get that out? You bring out Ohm's law and you just sum that around V over R and you get the current. And then the resistance rules, which are derived from these, okay, using Ohm's law into this one and into this one, gives you the rule for resistances in series, which is that the total resistance is the sum of the other resistances, and resistance in parallel, where you add the reciprocals, and the total is a reciprocal of whatever answer you get. So this essentially is your toolkit. Now I just want to briefly say about derivations, because one of the live feeds that I've done recently is all of the derivations that I could find in the Edexcel syllabus, basically. So I've gone through about 3/4 of an hour worth of derivations. So that's good, easy kind of revision that you can go through. You just watch that and think about that skill of derivation that's coming in the exam. So I think I'll just do one more little section, and then I'll have a quick look at the chat and tell you some more things about my live feeds and other things you can be doing to prepare yourself for tomorrow. All right. So I was asked to go through thermal physics and the gas laws. Okay, so I've just kind of picked out some key bits of this. So the first thing is specific heat capacity equation. Okay, thermal energy transferred to something to raise its temperature, or transferred away from it because its temperature is lowered. Okay, change in energy is equal to the mass times specific heat capacity times the change in temperature. And also specific latent heat, which is melting or boiling or any kind of change of state. And you need to recognize that when they give you latent heat of vaporization, that's between a gas and a liquid. Doesn't matter which direction we're going, it's between a gas and a liquid, either condensation or boiling. And then latent heat of fusion is between a liquid and a solid. Again, not mattering which direction we're going, but between a liquid and a solid. So it could be melting, it could be freezing. Okay, it could be energy in, or it could be energy out. Now, what I want to say about this is think about an energy analysis context with this, because these normally come up where they're not just asking you to work out the energy or work out specific heat capacity. That's too GCSE for you guys. But you're actually working out an energy and using that energy to work something else out. Now, I know on the Edexcel and in all the Edexcel core practicals video that I went through just the other day, another live feed that you can find in the description to this video, there is one where you actually figure out the latent heat of fusion for ice by equating it to the energy change in the liquid that you've melted the ice in. So it's quite a complicated practical, using an energy to work out another energy and therefore work something else out. And that is the idea of energy analysis, basically. Okay, so then there's this idea of internal energy. Now, internal energy, U, is defined as the sum of the potential energy between all the particles plus the sum of the kinetic energies of the particles. And this is a really good definition to remember. Okay, normally it's going to come out in words. They're not going to ask you to calculate too much in terms of numerically with this, although it could be involved with one of these parts of the energy analysis in here. What about those potential energies? Well, they're potential energies due to the fields of attraction or repulsion between the particles. And the kinetic energy is due to the speed of the movements. Okay? Now it could be, and this is an increase or a change in or a decrease of internal energies by two things: by heating, so Q we use to mean heat transfer, and by work, so that's forces acting upon the particles over a distance, right? So this equation is about how an internal energy changes, and this is the definition of an internal energy. So this is a really useful set of definitions. Now, I'm not going to go through this, but there's a spec point in most of the syllabuses, certainly in Edexcel, which tells you to derive this equation here. Okay. Now, you do that from Newton's second law, from some of the forces being equal to the rate of change of momentum, and you need to think about this c, the little c in those brackets, okay, and squared is what we call RMS speed. So the c means RMS speed, root mean square speed, and you square that in this equation. So the root mean square speed is basically looking at the vectors of all of those different particles that are moving around in 3 dimensions and bringing that down into just a kind of scalar form, if you like. I put a link in the description, not to one of my videos, but actually one of the Science Shorts videos, who's got loads of good videos, especially as well going through exams, and he's putting out loads of exam papers. So that's another tip if you want to spend the rest of the evening after this feed or early tomorrow just actually looking through exams. Watch all of his videos, watch as many as you can that you think are relevant to you, but be thinking about how he solves the problems, okay, that are in the question, not just what the answers are. How does he solve the problems? Okay, so you need to know how to derive that. Now the ideal gas laws are a set of 3 laws basically. Okay, so pressure is inversely proportional to volume, pressure is proportional to temperature, and volume is proportional to temperature as well. And what that means is, okay, as long as in this case the temperatures are fixed, as long as this case volume is fixed, as long as this case pressure is fixed, okay, that there's a constant relationship between them if the mass of gas is fixed and there's no loss of any energy. Okay, no transfer of energy out of the system, then these are the case. What it means is if we put those all together, that PV over T is equal to a constant. Now that constant in some exam boards is defined as NK, where N is the number of particles and K is the Stefan's constant. Okay, Boltzmann constant, my mistake, right? This is this one here. But in some exam boards and in chemistry, that constant is Rn, or the molecular gas constant, times by the number of moles. So just take the time before you go into that exam, whichever one you know that's coming up, to make sure you know exactly which exam board, which equation your exam board in physics likes. Most of the time in physics we use this one, where capital N is the number of particles. Okay, now NK equals NR. They're the same number, right? But N is the number of moles. Okay, so that by Avogadro's constant equates K and R as well. So just make sure you know which one you need to use. I think there might be some syllabuses where you have to actually be able to work with either anytime. Okay, so this is the one in Edexcel, for example. And then lastly, with the gas laws, before I have a look at some chat, then pressure over volume, this is the first one here. Okay, so they're inversely proportional. This is temperature versus power, so temperature is on the x-axis, power is on the y, and we kind of take readings of, sorry, my mistake, pressure is on the y. We take readings of temperature and pressure through the kind of normal atmospheric temperatures on Earth, sort of somewhere between 0 and 100 degrees Celsius, and we extrapolate that line back to absolute 0. So this is the point at which those particles would have no kinetic energy, and we know kinetic energy is proportional to temperature by this last equation we'll talk about briefly just in a moment. So this one is also volume proportional to temperature, but they don't go through the origin on these graphs, because the origin of these graphs is in Celsius. They go through the origin of a temperature graph, okay, where we use absolute temperature. And here's a little reminder: in thermal physics, whenever you see capital T, we're talking about absolute temperature. So it means convert into Kelvin by that figure 273 before you do any calculations. Okay, so capital T is used for time period in SHM and everything, but it's used as absolute temperature in terms of this. And be aware that this, one of the main contexts of this is going to be in terms of space. All right. So next one, derive, and again from the video that I've dumped in the description, which you can look at after the feed or after all of our feeds if you like. derive a half mc squared, which is the average kinetic energy of the particles, and that is proportional to temperature by the I think I put a half in the wrong place there, by the Boltzmann constant again. Okay, so that's that. Now actually Mr. Maths and Lewis went over these two laws. I don't know, I'll have a look in the chat. If you want me to just briefly go over these two laws, Boltzmann and Wien's law, then I will do, but I'm just going to pause because I've been talking for a long time to have a little look at the chat. Okay, so here comes a jump scare. If you're used to my things, then your volume's way up with your headphones, so you might want to just turn them down. Alright, you've been warned. 3, 2, 1. Okay, so let's have a little look through this chat then. I've seen already, this is neither exam board. I'm not focusing on any particular exam board. Alright guys, this is the one I teach is Edexcel, right, but it's useful for all exam boards. Some of it might not come up in your paper one, but hopefully quick enough, and if you ask me for things, then that's the things that we're doing, okay. Resonance, people want resonance, okay, so I could do that later on. Yeah, resonance is a good topic to have a little go through. Go through some hard electricity questions and further magnets. I'm not going to spend much time going through questions, right, but there are some of the hardest questions is one of the feeds that I've done over this week, so maybe check out those feeds, they're all in the description as well. Yeah, don't wait, look, just stop worrying about the exam boards so much. I know you need to know what's on yours tomorrow, okay, but let's just, at this half an hour you got with me, let's just ask good questions as well. Yeah, Ben Dunlop's having a really good chat through some potential divider questions. That's really good. What I've seen in my feeds, thanks Lewis, glad you enjoy my advice. What I've seen in live feeds is people actually going from those live feeds into group chat. So maybe you can hang out in the live feed after both of our things at the end of today, after my second one, and you can actually just say, well, who wants to go in the AQA group chat? You can make one of those. Right, okay, moving on. Resonance, again, people like that. Circular motion, I could do a little bit on that. Again, you'll find a lot of these stuff as videos as well, so why not check them out. What is absolute temperature? It's just temperature in Kelvin, basically. Okay, so it's an absolute because it's measured from 0 temperature, whereas 0 degrees C is just the temperature of the freezing point of water at standard atmosphere and pressure. Yeah, I noticed that 3/2 kT. Yeah, I noticed that as well. Most common topic types that exam board mix. Well, that's what we tried to pick out for these ones. Why exactly does LDR resistance fall when light intensity increases? My teacher said a fact, never explained. It's quantum, basically. It's a quantum effect. So there's a depletion layer between two bits of silicon. Okay, right. N-type and P-type, which some of you might know from those the GCSE topics. Okay, all right. N-type means that negative charge can move. It's got an excess of negative charge, basically, and the P-type means that positive charge can move. And there's a depletion layer between them, and it needs some energy to get across that gap, right? So the light intensity, the light, when you know about quantum, I hope, a photon comes in, gives its energy to an electron, and gives it the energy to jump across that depletion layer, that kind of magnetic, the kind of electric field that's stopping the charge moving. It's just like a diode, it's just like a thermistor, okay? It's all just different ways of getting the energy to initially jump across the depletion layer. So it's a quantum effect, basically. You can think about it like this in terms of the I-nave equation. Okay, do you know the transport equation? I is NAV and then E or Q, whichever exam board uses. The charge on charge carrier, it increases N. Okay, so when the light falls on the semiconductors, the silicon, it increases the number of free charge carriers per unit volume, and so the resistance goes down. All right, glad to see you, Mariam. Welcome. Okay, I started this about 20 minutes ago, and we're going to go across to Mr. Matheson once more after a couple more bits, and then come back to me after another half an hour. So I haven't seen anyone say, do they want me to chat through Boltzmann and Wien's law again quickly? And then I've got homogeneity of units, left-hand rule, and Archimedes' principle to chat through, so you let me know. Okay, and I'm going to get back into the visualizer just now. emission line spectrum is a good idea. Right, okay, so. Thank you very much for the super chat, PG. Okay, that qualifies as my first super chat. Okay, if you've got a question, then I'll make sure we'll go for that. Okay. Okay, money's not a big deal for me, but it's nice to have the recognition. It's really nice, as I said earlier. Yeah, SHM someone's asked for. It's really nice to have people appreciate it. They've also got a Patreon. I know this is going to be your last one, but if you want to check out my Patreon, I'm looking to develop my channel in the future, and if you've got ideas, then Patreon's the place where I'm going to be asking for feedback on some ideas that I've got for the next year and the year after that. And hopefully you guys are going to university, but maybe you would want to diffraction grating, yeah, okay, do that one. Maybe you would want to support somebody like me for the next generation in the future. Not when you're at university and you're struggling for money, but in the future, maybe, you never know. Okay, right, let's go ahead and go back into the visualizer for these bits, and then I'll be handing you back over to Lewis, and I will see you after half an hour. Right, so homogeneity of units. Well, my first question is basically about what is a what, right? So if they've given you this question, maybe they've posed you this question: what is a what? Or show that a what is equivalent to some other form of units, right? I know that's a silly question, right? But they'll often ask you to show that something is homogeneous with respect to units. Now, it's all about being able to take any equation down to base units, and I suggest that's something that you can do between today and tomorrow. Get your equation sheet, go through them all, or go for any that you struggle with, and actually take them down, either side of them, to base units. And that would be a really useful thing just for getting your head around what all those quantities are, and that you're ready to use them in the exam, right? So what you've got to do is you've got to think about getting to a set of equations, deriving a new equation which is all a base quantity, and the base quantities length, time, absolute temperature, current, okay, kilograms. Okay, so there's like 5 of them. I think I missed one out. Tell me what they are. You need to make sure you know them really well. But anyway, so you derive something that's only got basically base units. Okay, so what I've done here, work done is a force times a distance. Thanks, Mariam. Yeah, awesome. And a force is a mass times acceleration. Okay, so all I've done then is force times distance over time. That is what power is. So now I know all of those quantities have base units, right? So now I just sub them in. Kilograms meters per second squared is kilograms meters per second squared, and then meters for the distance, and then over seconds for time. And then I just simplify, okay, and ensure that what. So what is a watt? A watt is kilogram meter squared second to the minus 3. Moving on, this is the equation I was just talking about briefly. Okay, I nav, I call that the transport equation, is the proper name for it. Okay, I equals nqva, where n is the number of charge carriers per unit volume, the number of free charge carriers per unit volume. Q is the charge on one of those charge carriers, and it's usually an electron. That's why I call it I nav. It's just a way of remembering it, I-N-A-V-E, where E is the charge on an electron. And V is the drift velocity, and interestingly, the drift velocity in most conductors is very, very slow. And this is the area, the cross-sectional area of the conductor. Right, so you need to think about getting this down into base units. Now, as far as I'm aware, pretty much all of those are measured in base quantities, apart from Q. Okay, so Q comes from the equation current is charge over time, so Q is IT, so Q is AS, right? So an amp second. So here we go, now plug in all the numbers, all the equations, all these units that I know, and here's a tip as well. If you notice that I've got algebra for quantities on this side, and units on this side for both of these questions that I've just done. I'm not confusing, because you see I've got A for area here, and I've got A for amps over here. So I would just make sure that you keep things separately. And actually that's a decent tip, I think, but in those tiny little boxes they give you to answer questions in the exam, split it into 2 and work in 2 columns anyway. So in the charge carrier is just a number per unit volume, so it's units meters to the minus 3. Charge is a coulomb, okay, an area, charge is a coulomb, the speed is meters per second, and then the area is meters squared. Cancel all the m's, look, and you end up with coulombs per second, which is an amp by this one here. So this is a structured response showing us exactly what the unit amp is. How much time we've got? 4 more minutes, and then I'm going back to you, Lewis. Okay, if you're still there, my buddy. Don't worry about asking for money. Literally, it's not a big deal. If you go to, I don't know, private school and you've got Lambos outside, then maybe you ought to consider donating. But it's not a big deal. Right. Okay. So the way people asked about this, okay, the difference in left-hand rule, Fleming's left-hand rule for the motor effect, and the right-hand rule for EM induction, right? Now, it's exactly the same thing, it's just that you know that by Lenz's law, EM induction opposes the force that created it, right? The change that created it. Faraday and Lenz's law. Yeah, okay. So, how do we remember which one to use in which case? Well, in Britain, we motor on the left. Sorry if you don't live in Britain, but in Britain, we motor on the left, so that's the way I always remember it. But for both of these hands, both of these things for figuring out either motor effect or EM induction, then you just remember the thumb is F, first finger is field is B, and the second finger of the current is I, so F, B, and I. Okay, it's a really neat way of remembering them. Okay, so that's all that is. And then Archimedes' principle, and this is used in a falling ball viscometer, okay, is all about deriving an equation for V term, right? So you consider something falling through a column of fluid, okay, and when there's no friction with the outside of the thing. Okay, it has a weight, and if you've got a free body diagram, you always put a weight straight on, okay, as long as it's in space, as long as it's not in space or something, very far away from a large mass. An upthrust, okay, because there's some fluid being displaced here, and then the drag, which is what we call also the Stokes force. So we're actually going to use a little expression to say at V term, we know the forces are balanced, so at V term, the weight is equal to upthrust plus drag. So we're going to have to work out a little expression for all these. Well, here's the weight. It's a sphere, so that's the volume of a sphere, 4/3 pi r cubed. Rho is the density of the sphere. G is gravitational acceleration, so this is then mass times the gravitational acceleration. Okay, so that's that. And then the upthrust is the weight of the fluid displaced, okay, because there's a slightly higher pressure underneath it. So this is 4/3 pi r cubed, sigma, which is the density of the fluid, and times G. So this is the weight of fluid displaced, and this is the Stokes force, okay. F is 6 pi r eta, which is the coefficient of viscosity, which is what we want to get to an equation for, really, or V term. Okay, so we can manipulate either of those two things. If in a falling ball viscometer, this is what our target is. If we were just trying to work out what a V term should be, a terminal velocity should be, then our target would be V term. Right, so here we go, and then we just move all this across. It's added on this side, so it's taken away on this side. This is this line here. Then we factorise, look, so we take out all the common factors, and we get this, 4/3 pi r cubed G, rho minus sigma, okay, which is because there's that little minus there, and then the Stokes force bit. And then we rearrange by leaving V term, or we could leave eta incidentally, okay, you're just going to see that they're kind of, you can move them either side, and move that across here, so 6 pi r eta goes on the bottom line, cancel the things that are the same, including one of the r's, and then figure out the numbers, and you get this equation 2 r squared g equals rho minus sigma over 9 eta, and that is equal to V term. Right, that's a nice derivation that you can all get your head around. Can I go through the number of moles topic? Now it's a super chat, so I better have a little look at that one as well. Number of moles is something that never comes up in Edexcel, but I will have a little look at that. Okay, so I'm going to pretty much, apart from just to say one brief thing, if that's okay with you, Lewis. Okay, I won't be long with this. I'm going to pretty much just hand over in a moment, just to say that in the description is all the live feeds that I've had for the last few days. They are hardest questions in the A level was yesterday. Longer written questions and how to tackle those was a really useful feed. I felt people really kind of felt good about that one, so definitely check that one out. Every practical from Edexcel, but those skills are the same for all different exam boards. The apparatus and techniques are the same for different exam boards, so really well worth checking that one out as well, even if you're not in Edexcel. And all the derivations that I can find. So a whole video with all the derivations, which I suggest is a really good one for getting your head into that algebra space, because some of the hardest things you have to do is derivations. Right, I will have a look through those things people have suggested, and I will check you all out after Lewis's next half an hour. Right, thanks, over to you, bud.